Hello students. So now I am going to give a lecture on the last and final module of Geotechnical Engineering 1, which is slope stability and compaction. So what is a slope? A slope is an exposed ground surface that stands at a particular certain angle with the horizontal. There are two types of slopes. There are naturally occurring slopes. Like in the case of mountains and valleys, we see they are naturally occurring slopes. And there are also man-made slopes like the railway embankments, the embankment for highways, earth dams, canals. All these are man-made slopes. So now in this particular module, we will be dealing with different types of slope failures. How to find the factor of safety for a particular slope. How to find the limiting height of a particular slope. And also various graphical methods to do the slope stability analysis. As far as a civil engineer is concerned, the slope stability is a very important area because all the disasters, they all cause, maybe due to human activities or due to natural calamities. Whenever a landslide occurs, it is all causing huge death and damage. And as being a civil engineer, you must be very shrewd in designing the slopes, or even if you make a cuts for any construction purpose, it must have proper stability. So here just I am reading a very important sentence. Slope stability analysis consists of determining and comparing the shear stress developed along the potential failure surface with the shear strength of soil. So what this particular sentence means is that whenever you design any slope, whenever you prescribe a particular angle, sloping angle for any soil, that particular potential failure surface, the shear strength of that potential failure surface or that area zone, that must not exceed the shear strength of that particular soil. Okay, so that is very important. And here in the picture you can see a landslide occurred in Wayanad. Here it is also as due to a lot of extensive quarrying. Such landslides occurred recently in Wayanad in the recent rainfalls. So being a civil engineer, we have a social responsibility as well, apart from just studying this topic. So here also you can see some of major slope failures clearly in this both these pictures. You can see that slope failure, how it is occurring and how disastrous it can be. So now the different types of slopes. There are two types of slopes: infinite slopes and finite slopes. So finite slopes have large dimensions and they extend over a large distance, and the soil mass is always inclined to the horizontal. So all the naturally occurring slopes, most of the naturally occurring slopes, the slopes of mountains, valleys, and all these slopes are infinite slopes. Now finite slopes. In finite slopes also there are naturally occurring slopes, but all the man-made slopes are finite slopes. So in finite slope, it is a slope with fixed height and it is having a base and a top surface. For example, the inclined faces of earth dams, embankments, excavations, these are all finite slopes. So you can see here in the figure examples of finite slopes or man-made slopes. Highways, you can see highway embankment here. Here you can see the railway embankment. You can see there is a slope which is very finite. It is not extending to a great distance. You can see the slope here for an earthen dam, a slope given for river training work. River training work is actually a way to divert the direction of rivers in order to prevent floods and erosion, soil erosion, etc. So this area comes in the hydraulic structures and all. You will be studying it in the next semesters, but here also you can see it's like quite a not a steep slope, but a gentle slope is maintained in river training. So these are all examples of man-made slopes or infinite. Sorry, these are all examples of finite slopes. Now let's see what are the triggering mechanisms which lead to slope failure. So all we know what is happening around us. They are all the reasons for slope failure. First one is intense rainfall, which we have witnessed in 2018 and 19 in our state. Then the changes in the water level, and this is applicable for earthen dams and all. Then seepage water flow, when the water seeps through the foundations of dams, earthen dams. Volcanic eruptions, the tremors can lead to instability in the slopes, earthquakes, and human activities. Human activities nowadays contribute to a large extent in the failure of slope. Next comes the types of slope failure. So this is a very important university question, almost frequently asked to explain the different types of slope failure. It is easy to learn also, and whenever you answer such types of questions, always draw figures, because figures give you added marks. So there are 4 types of slope failure. First one is the rotational failure, then comes translational failure, then comes compound failure, and the last one is the wedge failure. So first let us discuss translational failure. Translational failure usually occurs in infinite slopes. That is, this failure occur in the natural slopes, and it always occur in a direction parallel to the slope. Okay, so this is all about translational failure, and here in the figure you can see in the left hand side of the slide how this failure is occurring. So whenever, again I am repeating, whenever you answer such questions, always you draw figures which will enhance the chance of scoring marks. So next topic is the rotational failure. So before going into the details of rotational failure, I would like to show you 2 key parts of a slope. So here in the figure you can see I have circled in the orange color here, which indicates the toe of a slope, and the red color slanting line you can see here in the last figure, base failure, which is shown as face. It is the face of the slope. So you must be very clear about the parts of a slope if you are going to study this particular type of failure. Now let us move on to the different types of rotational failure. So the first one is the face failure. So that you can see in figure B. There is some problem in the arrangement of the figures. So in figure B you can see the slope failure or face failure. So here it is actually the face of a slope is undergoing failure. So this usually occurs when you have a strong soil at the toe portion, and also the slope is quite gentle. It is not a steep slope. In such cases the failure is called the face failure. Now comes the toe failure, that is figure A. In toe failure, the failure surface pass through the toe of the slope. This usually occurs in soils which are homogeneous in nature, that is the same soil is having throughout the slope, and also the slope is steep. And the last one is the base failure. So in base failure, the failure surface passes below the toe, and this usually occurs when you have a weak foundation below that slope, or below that slope you have a weak soil deposit. Okay, so these are the 3 different types of rotational failure. So here in the slide, the figure in the left side of the slide, you can see rotational failure, actually what is happening in the field. So you can see here it is an arc portion which is being failed and slipping down. So that is why it is called a rotational failure, unlike the translational failure, because in translational failure the failure surface is a horizontal line. Okay, so next is compound failure. So I already told you compound failure is a mixture of 2 failures, that is a mixture of rotational failure and translational failure. So the figure also you can see here in the right hand side, that is here in a particular failure where it extends the toe of that slope, the failure surface, and you can see the bottom surface is a flat surface and the two ends are curved. So this is an example of compound failure. So in the figure also you can have that difference, that is always the bottommost portion of that failure surface will be a flat surface. Then you can say that it is a compound failure. Now the last one is the wedge failure. Wedge failure is also known as block failure or plane failure, and this is generally an inclined failure plane, as you can see in the figure. So this usually occurs when there are fissures or joints, and also when you have a weak soil layer in a slope, and also when you have a slope with two different materials, such kinds of wedge failure is observed. So here in the figure, in the left hand side, the topmost figure, you can see how a wedge shaped portion is slipping from that slope. So this usually occurs very similar. This is a very similar case to that of a translational failure, but only difference is that translational failure is usually occurring only in infinite slopes, but this wedge failure you can observe in both infinite as well as finite slopes. The topic is the slope stability analysis. So before going to the slope stability analysis, let us discuss a few points. The stability of slope depends on the stress developed and the strength of the slope. So whatever stress is developed in that failure surface, and whatever the strength you have, inherent strength of that particular soil of that slope, so the stability depends on these two factors. Then the ratio of strength to the stress developed is defined as the factor of safety of slope. So whenever the strength of the particular soil is higher than the stress developed due to that potential failure surface, then the slope is always safe. Or you can say that the slope is stable only when the factor of safety is greater than 1. This is very important. It must be always greater than 1. Once it is 1, once the factor of safety is 1, that means the slope will start to fail. So how you compute the factor of safety? So factor of safety can be computed in terms of shear strength of the soil. It can be computed in terms of the cohesion of the soil, or it can be computed in terms of the frictional resistance or angle of internal friction of that particular soil. So all these types, three different factor of safeties, they have the same weightage. Whether you compute it based on shear strength or cohesion or friction, the weightage is same, because all these factor of safeties must be greater than 1. Then only you can say that your slope is safe. Now first let us discuss factor of safety with respect to shear strength. It is defined as the ratio of shear strength of soil to the shear stress developed. So here you can see the equation. Factor of safety with respect to shear strength is denoted as F suffix S, which is equal to capital S by tau suffix M, where capital S is the shear strength of the soil and tau M is the shear stress developed or mobilized shear strength, or that is the shear strength developed by that potential failure surface. So the shear stress developed within that potential failure surface must be always less than the shear strength of the soil. Then you can say that the slope is safe. Now you already know what is the shear strength of soil. It is denoted as S is equal to C plus sigma tan phi. This you have already studied in the 4th module in the Moore-Coulomb failure criteria. What is the shear strength of soil? The major shear strength parameters of soil are the cohesion of that particular soil C and the angle of internal friction phi. So when this shear strength is mobilized, that is when a failure surface is developed and it creates some stresses to drag that particular surface, that failure surface, then that value, when it is equal, or that value is tau M, when tau M is equal to the shear strength of that particular soil, then the factor of safety becomes 1, and again when tau m is increasing, then you can say that the slope is in unstable condition. Okay, so now we will discuss the factor of safety with respect to cohesion and factor of safety with respect to friction. So here you can see here factor of safety with respect to cohesion is denoted as Fc, and factor of safety with respect to friction is denoted as F5. So in both the cases, it is the ratio of the cohesion of the soil to the mobilized cohesion of the soil, and in the second case, that is factor of safety with respect to friction, it is the angle of internal friction of the soil to the mobilized angle of internal friction of the soil. So just bifurcating the initial factor of safety, initially it was based on the shear strength. Now we are bifurcating in two different factor of safeties, one in terms of cohesion and one in terms of friction. That is the only difference. Okay.